Alright, so today we are finishing our discussion of representations of SL2 with a single topic, which was promised earlier, I believe, and that is determination of the highest weights. And it comes with a theorem. Let chi be an element of H star as chi of a sequence of lambda I is just equal to the sum of ui lambda I for some ui sequence. And there exists an irreducible G module with highest weight chi if and only if ui minus uj is a positive integer for all I less than j. Proof, and we're doing that it's necessary only. We have that ui minus uj. We have that ui minus uj is equal to chi of h of alpha when alpha is the positive root of lambda I minus lambda j. Hence, we need that this chi of h alpha is a positive integer for alpha in R positive if chi is the weight of a primitive element V. And this is a proposition attached. Going to let V be a primitive element of weight chi, and then we're going to define V alpha m to be x negative alpha to the m times V over m factorial for m greater than or equal to 0, where the m is just the mth iterate. Then we have the following. First off, x negative alpha v to the alpha m is equal to m plus 1 of v alpha m plus 1. Condition 2 is that h v alpha sub m is equal to chi minus m alpha of h V alpha m if h is in our diagonals. And thirdly, chi alpha V alpha m is equal to chi of h alpha minus m plus 1 times V alpha to the of m minus 1. And so condition 1 is immediate from the formula above. We get 2 means that V alpha m is of weight chi minus m alpha, as we have seen. We're going to show the third condition by induction on m. Induction on m with once again m equals 0 is going to be trivial. If m is greater than or equal to 1, then we have that m of x alpha V alpha m is equal to x alpha x negative alpha V to the a of m minus 1, which is equal to h alpha on v m minus 1 alpha plus x negative alpha x alpha v to the alpha of m minus 1, which is just giving us lambda v alpha m minus 1, where lambda is equal to chi of h alpha minus m minus 1 alpha of h alpha plus m minus 1 of chi of h alpha minus m plus 2. And since we know that alpha of h alpha is just always 2, we get that lambda is equal to m of chi of h alpha minus m plus 1, and that gives us our third condition, and so we're done that part. Then we have a corollary. Which states there exists non-negative m such that V alpha m is non-zero and V alpha m plus 1 is 0. Then we have that chi of h alpha is m. The proof: since the V alpha of m's have weight of chi minus m alpha and the number of possible weights of your modulus finite, we have that V alpha of m is 0 for large m, hence the existence of m as above. By our third formula from above, for m plus 1, we get that 0 is x alpha of v alpha m plus 1 as above, which is chi of h alpha minus m times v to the alpha of m. Since v alpha m is non-zero, this gives that chi of h alpha is equal to m. Now, thus we have necessity. Necessity. Now, we need sufficiency, and I also need to rearrange some stuff here. So give me one moment, please. Now, proof of as above of this is, in this case, it is sufficiency. Let each pi I be the sum of lambda I and lambda j from 1 to I. Then our theorem states that chi can be written as chi is the sum of from 1 to negative 1 n minus 1 of mi pi I. For mi positive integer. This motivates the proposition. Chi and chi prime are highest weights of irreducible modules v and v prime. Then chi plus chi prime is the highest weight of a submodule of v tensor v prime. Proof. Let v and v prime be primitive elements of v and v prime. Then v tensor v prime is a primitive element of v tensor v prime with weight of chi plus chi prime. And so the proposition holds for the irreducible G submodule generated by v tensor v prime. And that comes with a corollary. Which states the set of highest weights is closed under addition. Hence, we can show chi is a highest weight by showing that the pi i's are highest weights. Weights by giving explicitly their irreducible G modules. Comes a proposition. Let V be k to the n as a G module for I from 1 to n minus 1. Let Vi be the exterior ith power of V. Then Vi is an irreducible weight. No, it's not an irreducible weight. That doesn't make any sense. It's an irreducible G module of highest weight pi sub I. And this is our last proposition. Our proof. Let EI from 1 to n be the canonical basis of V, with Vi being the wedge of E1 through EI. Then by computation, Vi is a primitive element of Vi of weight pi I. By applying to Vi a monomial in x minus alphas, we can obtain any element of the form em1 through emi, with m1 ordered to mi. Hence, Vi is irreducible. And we have our original theorem proven. And there's a few remarks to be made about this, and then we'll be closing out this section. Probably a shorter video, but I mean, the last two were like hour-longs each, right? So, remarks. We have analogous results. For any semi-simple Lie algebra. In fact, this whole thing was kind of a warm-up exercise for what we will be working with, I believe, tomorrow. where we'll be starting to get into like roots and root systems and that in like a more formal general context. Everything here applies in a general term to the general case, but we will be doing that all in a more formal context later on. And we saw that the classes of irreducible systems man, I'm not reading right today. Classes of irreducible G modules are in one-to-one correspondence with the systems of n-1 positive integers. And it says that there's an explicit description in Weil's book, The Classical Groups. And in one final remark is in the two-dimensional case, which we are largely interested in, there is just one integer m with its corresponding irreducible module as the mth symmetric power of V being the square of our base field. And that is actually the end of everything for groups in both Serre and now Bourbaki. We're getting into Freely algebras, but I think up next we'll be going into root-space decomposition in a more formal context. I am stalling out a bit here because this ended up being a lot shorter than I anticipated, but I mean, we had like 2-hour-long videos, right? Like I'm aiming for what, 2.25 hours a day, and I've gotten like 2 hours from the first 2 videos, so maybe having like a 20-minute video is a nice change of pace, kind of evens things out, evens out the average. I do want it to be a bit longer, so I'm stalling a bit here, but yeah, let's call it here.